Okay, so in 1.3, we're going to start talking about graphs of functions, and we'll see them and look at all the details of that. So graph of a function are all the points x comma f of x that were in the function. So it's just the curve. The greatest integer function, this is a new function we're going to briefly see and talk about, that just rounds a number up to the next closest integer. So in that function, if I put 1.1, 1.1 gets rounded up to 2. It will make something that looks like steps. That's why it's called a step function. And that takes us, yes, to the next definition. Even functions are symmetric with the y-axis. Odd functions are symmetric with the origin. And that goes to their power. So an even function would be x squared. X cubed is an odd function. It matches the symmetry we're talking about. Okay. So here with this, when we talk about closed and open circles on graphs, so these are going to come in very handy with piecewise functions. Open circles will mean that it appears to be, to approach, a point, but is not equal to it. A closed circle means it can actually equal that number. So if we're restricting a domain and I say x is greater than or equal to 1, whatever that y value is for when x is 1, we're going to put a closed circle. If I just said like x is greater than 1 without the equals underneath, we'll make it an open circle. How do you find the domain of a function? We look at its x values. So domain is the x values. And for a good number of functions, it will be, why is it not pushing notifications? So to the guys that just got in, I will fix your attendance in a minute. I'm sorry if you were waiting too long. It did not alert me. So the domain is all our x values. Oftentimes, this will be all real numbers, but sometimes it's not. We just have to look at it. The range are the possible y values. Now, the y values can vary quite more than just usually defaulting to all real numbers. That's fine. That's fine. It happens. So the y values like on an x squared, since that has a minimum, it's going to be like y is greater than 0. But for a linear equation, it will be all real numbers. So let's go to here. And sorry, I think I accidentally put yesterday's due now, or not yesterday's due now, yesterday's exit ticket about this, the vertical line test. From what I saw, the few people that did it when I graded it early in the afternoon got it, but I just realized this was where we talked about the vertical line test. So the vertical line test says if a vertical line crosses a graph more than once, then it is not a function. So what I'm going to do to determine if these are functions is I'm just going to draw vertical lines. If each line only crosses once, great, it is a function. If I see a line cross more than once, it is not a function. It's that simple. So let me actually use the line tool on this. So I can draw some vertical lines in here. Are any of these lines crossing this more than once? No. So we passed the vertical line test here. So it is a function. Now let's look at the next one. What happened when I drew a vertical line through this one? Yeah, it crosses over here and here, right? So it fails the vertical line test. So this is not a function. So that's all the vertical line test is. You probably did see that at some point in IM3. You know, it's a rather easy test. Just draw a line. If it crosses more than once, just say not a function. That's it. If it says explain, you could simply say failed the vertical line test. That is an appropriate statement there and will be very well understood. Okay. Here with this is very formal here. I'm also going to break it down into less formal mathematical terms. So a function is increasing if for any interval x1 and x2, the interval, so this needs to be happening. If x1 is less than x2, then f of x1 also has to be less than f of x2. Basically what this is saying, x1 is less than x2 going left to right. The y value, so the first y value is smaller than the next y value. Basically, if it's increasing, it's going up as we read left to right. We'll notice for decreasing, this inequality sign gets flipped around. That means your earlier y value has to be bigger than your next y value. Again, as you're reading left to right, it's going downhill. For something to be constant, those y values need to be the same. So it's going to be level if it's constant. So I know this is stated very formally mathematically here. I'm just trying to get you used to this because when you take calculus, you're going to see, you know, things written more formal like this mathematically, as opposed to just being like, oh, increasing it's going up, decreasing it's going down. Okay. Again, so again, that summary here, where it goes up, moving left to right, that's increasing. Where it goes down, moving left to right, it's decreasing. And if it's a horizontal line, that means it is constant. So again, that is just a summary. Oh, I missed that then. That's just a summary of that. So, what the high turning point, low turning point. So max and mins. A function f of a is called a relative min if a relative min of f if a is a low turning point. It's a max if it's a high turning point. Local max, local min. You've seen parabolas before. It's just going to go kind of with our common sense. Low points the min, high points the max. Any questions on this so far? I know this was a lot of just me talking. Okay, so how to approximate these using a graphing calculator? We're going to work it with Desmos. So for Desmos, it's super easy. graph it. And click on the max/min. So it is that simple for Desmos. I'm going to demonstrate that right now. There's Desmos. So I could say y equals 2x cubed, 2x cubed minus 4x squared plus 3x, no, just plus 3. I can click on my max. That's my max. Click here. That's my min. TI calculators, it is more complicated than that. If you're using TI 8384, Inspire, whatever, if you're using that instead of Desmos and want more instruction on it, please just let me know and we can arrange that like within office hours or something. But Desmos is super easy with it. Just click on it and it tells you. Okay, so let's look at this example here. Suppose that a function C represents the annual number of cases of chickenpox reported in reported for the year X in the United States, 1960 through 2000. Interpret the meaning of this being a minimal. So if it's a minimum, am I going to be at a high point of chickenpox or a low point of chickenpox? Low point. What does 1998 mean in this context? Yeah, it's the year where it's at the low. So the 3 will represent 3 million cases. So let's just write that down. So what does the meaning of this being the minimum? It means in 1998, we saw a low of 3 million cases. And that's it. That's all interpret the meaning was there. So again, that was just trying to read into the context of the problem and all that. Okay, a step function. It's sort of like a piecewise function. It's what we're going to use to introduce piecewise functions a little more. So a step function rounds a number up. So this is the greatest integer function. So each of these is getting rounded up. So if I'm at like 1.1, that gets rounded up to 2 and so forth. So we call it a step function because it looks like steps. Okay, so here, find this one. So find this. So f of 3.74 is equal to, so I'm using that step function. All I do is round this up. When I round that up, that's 4. So if we're using the greatest integer function, it says, hey, whatever you have, round it up, no big deal, that's it. Now let's look at where we're going to have probably the biggest struggle here. Piecewise functions are a little bit of a pain to graph. Honestly, if you can graph them on Desmos, well, I'll take it because I know this is something students struggle with. So if you graph it well on Desmos and you want to take a picture of that or send me a picture of your Desmos, great, you can do that. I'm going to show you how to utilize Desmos to help us graph it by hand. I'm going to use a blended approach with it instead of doing it all by hand, just because I know this is tough for you guys. So here with this, my first function is a linear function. You can start at the y-intercept of 3, and then it goes up to over 1. Now, x is equal to 1. X is equal to 1 is right here. That is my critical value. So since this has a line underneath, I am going to draw that as a filled-in circle. Now here, what I'm going to do, since it's all the values less than 1, it's technically a straight line like this, ending at x equals 1. Again, we're going to see this on Desmos. So here with this, I'm going to start with a piecewise functions. We're going to use different letters for each part. So I'll start with f of x is equal to, that was 2x plus 3. But it had that restricted domain. So when I go back here, I am going to take what it says after the comma, and I'm going to write that in curly braces. Curly braces can be found on the keyboard if I hit A, B, C, and go here on the on-screen keyboard at the bottom row. If you're using typing on your keyboard, it will be Shift, and then square brackets are found to the right of P. So that said, x is greater than. If I need the line underneath, I could just hit equals behind it, and Desmos knows, oh, greater than or equal to. Oh, sorry, it's not greater than. It said less than, didn't it? Yep. Less than or equal to 1. Whoop. One too many of those. We'll mess that up. And there we go. We see this getting cut off, just like my graph, my hand's cut off right now. Now the green one, I'm going to do that just slightly differently. We're going to start with the Desmos of that. So that I could call now g of x equals, that was negative x plus 4. So we see this, but I did not put my restriction in there. That is x is greater than 1. And now that gets cut off here. So here we can now, I'm going to show you how we can make a table. I can say y equals f of x, and that just regraph that. I don't need to see it. I just want to make a table, so I can hit the gear and hit table. So notice all of a sudden this becomes undefined at 2. If I want to add more values into this table, like -3, -4, I can. If I want to try and see what 3 would be, that's undefined. 1.1 is also undefined. Now I'm going to make a table here. I could say y equals g of x, and then hit this, do the same thing. I don't need to see it. But I can go here and then hit table here. And now I got the table for this one, and we can see those points on there. Notice it's undefined until 2. If I put things in like 1.1, I get that value there. So it looks like, okay, 1.1 was 2.9. It looks like this point's right around 3. So we'll have an open circle there at 3. And actually, see if I do this, we'll see 1 comma undefined, but the second I move my finger away, it's just about a 3. I know that's a little hard for you guys to see physically here, just because it's a little faint, but I can make up more points in this table too if I wish. Again, if I try and be like, oh, -5, that's undefined because that's not part of our domain, but 5 is, 4 is, we can just get points like that. So if I wanted to share this, I can hit the share up here. You can email me a link. You can also export an image. So you could export this image and download it and send that to me as well. So this part had an open circle at 1 comma 3. I had like the point 2, 2. I had 3, 1. So it looks something like this. So that's graphing it by hand as well. I know piecewise functions are not pretty or easy. Please just try your best with them. I know they're a relatively new concept, but it takes a lot of old things you knew and kind of brings them together in a new way. It's going to be with every lesson, and I know it is a little bit of work, but warm up and do now are fast. Those 3 are fast. I'm not saying it isn't a significant amount of work. I'm not arguing you on that. But actually, I'm trying to make some of these lessons span more. I'm already seeing 2 days might be the better time frame for some lessons. So 1 homework might not be due for 2 more lessons. And it will get repeated in the following day's folder, just as a reminder, this is the work you need to get done. I know the homework will take you more time though. So even in odd functions. So a graph that is symmetric about the y-axis is an even function. So an example of an even function, let me pull one up on Desmos. I can delete out this. So an even function, y equals x squared, it is symmetrical about the y-axis. So if I go x equals 0, whoop, x equals 0, this black line, the blue is symmetric about this line. That's what it means to be an even function. To be an odd function, it needs to be symmetrical about the origin. So that'd be like y equals x cubed. So the red is symmetric about the origin. If I were to look at this again in respect to the origin, that's where this is symmetrical with like this area matches this area. A graph that is symmetric with respect to the x-axis is not a function. A function is even if f of negative f is equal to f of x. A function is odd if f of negative x is equal to negative f of x. Again, we'll just look at them with just the powers though. So I do want to show you something that is not a function. And that's the cool part about Desmos. It will let me graph things that are not functions. So if I say x equals y squared, this blue graph here is not a function. It would fail the vertical line test. So this is one that is symmetric about the x-axis, but it is not a function. Whoop, weird. Oh. Okay. Sorry, my smart notebook is wanting to act up right now. I don't know why. Okay, that was it. That's what I thought. Okay, so here, that was the end of this. Here is the homework assignment, so please give those a try. I don't think I put the due date until next Tuesday. It's either Monday or Tuesday when the due date is. So please make sure you are getting that done. Where's recording? Stop recording.